What is active transport? It is any type of movement of ions or molecules against their gradients. The antithesis of active transport, as we talked about in the previous video, is passive transport. And the main delineating factor is against the gradient. Active transport moves against the gradients. Passive transport moves down gradients. Because active transport is moving things against their gradients, it requires some form of energy. So as we look at this, there are going to be two forms of active transport that we will talk about. The first one is primary active transport, which utilizes chemical energy, generally in the form of ATP, and secondary active transport, which utilizes kinetic energy. The kinetic energy derives from an ion or molecule moving down its gradient. An ion moving down its gradient, let's say sodium moving into a cell passively down its gradient, is going to create kinetic energy, the energy of motion. That energy of motion is kinetic energy, like a ball rolling downhill could displace something in its way. Secondary active transport utilizes kinetic energy, whereas primary active transport utilizes ATP. The hydrolysis or breakdown of ATP will release energy, and that energy will be used to move things against their gradients. Primary and secondary active transports will move things against their gradients. Now let's take a look at the most common or popular of primary active transport that we will look at in this course, and that's the sodium-potassium pump that we see here. Now, to be clear, this symbol right here with the number is suggesting primary. Later, we're going to see a 2 in front of that symbol. It's going to refer to secondary. So we're talking about primary active transport in this. The sodium-potassium pump, otherwise known as the sodium-potassium ATPase, pumps 3 sodium out of cells against its gradient, against sodium's gradient, and 2 potassium ions into the cell against potassium's gradient. Because it's moving things against its gradient, it requires energy, and that energy is going to be ATP. The sodium-potassium pump is an enzyme that breaks down ATP, liberating energy from the ATP molecule or from the hydrolysis of the ATP molecule, and uses that energy to push these things against their gradients, pushing sodium out of the cell and potassium into the cell. Keep in mind, as we've elaborated at length already in this course, there's always a high concentration of sodium outside of the cell versus inside, and a high concentration of potassium inside of the cell versus the outside. So the role of the sodium-potassium pump, one is to maintain chemical gradients. And I'm going to go into more detail in this in a subsequent image here. But if sodium is moving into a cell, which it is doing constantly in our body cells, all day long, all minute long, there's leakage channels that allow sodium to move in. There's gated channels that allow sodium to move in. If sodium keeps moving into the cell, then that concentration gradient is going to diminish for sodium. And the same thing occurs with potassium. Potassium at times is going to be leaving the cell down its gradient. The more potassium leaves the cell, the more that gradient diminishes. So the sodium-potassium pump, by putting sodium back where it belongs, if you will, in the extracellular fluid, and moving potassium back where it belongs inside the cell in the intracellular fluid, that is maintaining the chemical gradients of sodium and potassium. Another role of the sodium-potassium pump is to preserve the cell voltage. Once again, the voltage is the difference in charge between the outside of the cell and the inside of the cell, And in a resting cell, that's negative in the interior, positive on the exterior, roughly negative 70 millivolts in the interior. It preserves that voltage or difference in charge merely by pushing more positive charge out of the cell than the positive charge that we're bringing in. If we're throwing 3 positive charges out of the cell and only bringing in 2 positive charges into the cell, that's making the exterior of the cell more positive. And the corollary of that, it's making the interior of the cell less positive. So it preserves the cell voltage. To be clear, it doesn't create the cell voltage, but it helps maintain it. And the third role of the sodium-potassium pump is to regulate cell volume. Volume is dictated for cells based on the amount of water that's moving into cells or out of cells. If there are more ions inside of the cell or solutes inside of the cell, water is going to keep moving into the cell, and the cell is going to start to expand, which we do not want. If there are more solutes out of the cell in the extracellular fluid, water is going to have a tendency to leave cells, and the cells are going to shrink. We don't want that either. We really want that isoosmotic environment where there's equal solute concentrations in the extracellular fluid as in the intracellular fluid. And if we have that, we are going to maintain or regulate the cell volume. Okay, so let's just take a look at this in a little bit more detail. Here we have an excited cell. I've used the term excited in previous videos, and what that means is the cell has undergone a change in voltage or it has depolarized. And we'll talk about action potentials and depolarizations and repolarizations in later videos. But a depolarization event is where the interior of the cell, in this case, becomes positive 30 millivolts. And cells become excited when they are trying to carry out some downstream activity. So muscle cells, for example, will undergo depolarization events to allow them to contract. Nerve cells will undergo depolarization events to allow the release of neurotransmitters to send some sort of signal from one part of the body to another part of the body. So this is an excited cell. How does it become more positive inside the cell? Keep in mind that a resting cell will look something like this. And this is something we've outlined, that there's a high concentration of sodium outside and a little concentration of sodium inside, or a smaller concentration of sodium inside. And the corollary, once again, is true of potassium: high concentration of potassium in the cell, low concentration of potassium outside of the cell. If sodium keeps moving into the cell, if the positive cation keeps moving into the cell, it's going to cause that cell to become more positive or excited. And that's what's known as a depolarization of a cell. So that's what we see right here. Positive charge, that this cell is excited. Now, one thing you may notice here is we do not have as large of a gradient for sodium right now because sodium came in to depolarize this cell. Now, to be clear, this is dramatic. During one depolarization event, during the influx of sodium coming into a cell, it's not going to disrupt the concentration gradient or the chemical gradient of sodium nearly that much. Very, very, very little, as a matter of fact. And the best example I've ever heard of this came from I believe, a medical physiology textbook that equated it to grains of sand. If you're at the beach and you're sitting on the beach, running around on the sand, there are trillions upon trillions or quadrillions grains of sand, quartz granules that make up the sand. But it only takes one of those quartz granules to get into your eye to irritate your eye. And the same thing applies to the depolarization or the excitation of a cell. That is to say, It only requires a small amount of sodium rushing into the cell to cause it to lose its difference in voltage or to cause it to depolarize. So one depolarization event is a non-factor. It's not going to disrupt the chemical gradient. But keep in mind, just in this time you've been listening to me talking in this particular image, you have probably had, I don't even know, thousands, tens of thousands of action potentials in your total body cells, whether it's your skeletal muscle, the neurons in your brain firing, your heart, the muscle cells of the heart, the autorhythmic cells. This is happening every day throughout the cells of your body. So this image of the loss of the chemical gradient of sodium, or not as great, there's still in this image more sodium outside than inside, is dramatic, but I'm just trying to highlight the point. If this happens over and over and over again, the chemical gradient for sodium is going to start to diminish. And the same thing is going to happen with potassium. Now, we are back to the polarized state. If a cell depolarizes, like we saw in the previous slide or the previous image, it becomes positive. But we always want that cell to return to its resting state, and that process is known as repolarization. This cell has now repolarized, moving back to negative 70 millivolts. And to achieve that, potassium keeps leaving the cell. Just like during depolarization, sodium kept coming into the cell. But as potassium starts leaving the cell to repolarize the cell, we also start losing the chemical gradient of potassium, which I've tried to illustrate here. There's not as high a potassium concentration inside the cell as there outside. These are somewhat equal now. Still more inside the cell, not as significant as before. So we want to return these chemical gradients back to this cell, which means we need to push sodium back out of the cell where it belongs and potassium back into the cell where it belongs. And that is achieved by the sodium-potassium pump. 3 sodium pushed out, 2 potassium pushed in. Now, going back to the third role of the sodium-potassium ATPase, which once again is the same thing as the sodium-potassium pump, maintaining cell volume. And we talked about the desire to have the extracellular fluid and the intracellular fluid being isoosmotic. So this may be confusing because we're throwing 3 solutes out and 2 in. Now keep in mind there's going to be more than one sodium-potassium pump in these cells. So this is going to be happening over and over again, and there's going to be a number of them. So we're not just dealing with 3 and 2. But to keep things simple, throwing 3 solutes out of the cell and throwing only 2 in, that is not suggesting or indicating that we have achieved isoosmolarity, because there would be more solutes outside of the cell than inside of the cell. But we have to remember the interior of the cell has protein anions and phosphate ions, which also function as solutes. So that's going to balance out this equation, creating an isoosmotic environment for these cells of our body. Okay, one last thing I want to highlight with regards to the sodium-potassium pump. I have mentioned you can call it the sodium-potassium pump, or you can refer to it as the sodium-potassium ATPase. Anytime you see the suffix ASE, that's suggesting we're dealing with an enzyme. This enzyme is going to break down ATP to liberate energy to pump things against their gradients. Later on in subsequent videos, we are going to encounter what is known as the ATP synthase, which is absolutely not to be confused with the sodium-potassium ATPase. They are 2 absolutely different things. That is to say, the sodium-potassium pump or the sodium-potassium ATPase actually breaks down ATP. But the ATP synthase is what builds or creates or synthesizes ATP. And we find this in the mitochondria of our cells. We're going to talk about it at length, but I just want to be clear, the ATP synthase is not the same thing as the sodium potassium ATPase. Now let's take a look at secondary active transports. Once again, there you see the two with the little circle up there in the superscript. That means secondary active transports. Here we're dealing with moving things against their gradients, but not all things. So in this image right here, we can see there's a high concentration of sodium outside of the cell and a low concentration of sodium inside of the cell. Low concentration of glucose outside of the cell, high concentration of glucose inside the cell. That's not the case with all body cells. There are certainly body cells that have low concentration of glucose inside of them. As a matter of fact, most of our body cells have low concentration of glucose. But there are certain regions of our body where there is less glucose in the extracellular fluid than in our cells. And some of these cells use secondary active transport to move glucose into body cells. For example, in the proximal convoluted tubule of the nephron in our kidneys, we'll get to this in a few months, they move glucose against their gradient into the cell by means of secondary active transport. And the transporter that does this is the sodium glucose transporter. And we mentioned this in previous videos. Sodium glucose transporter moves glucose against its gradient into the cell. Where is the kinetic energy coming from to move glucose into cells? It's coming from sodium. So sodium and glucose are moving together into the cell. Sodium is moving down its gradients into the cell, and in the process of moving into the cell, down its gradient, it's creating kinetic energy, which glucose harnesses or utilizes to move against its gradient into the cell. This is what's known as a co-transporter, specifically a symporter, because it's moving two entities, two things, sodium and glucose, together in the same direction into the cell. There are some co-transporters that are antiporters that move something down its gradient into the cell and something against its gradient out of the cell, or vice versa. So the secondary active transport is utilizing kinetic energy to move something into cells or out of cells. Keep in mind, during secondary active transport, there are going to be two things moving. One thing moving down its gradient, creating the kinetic energy. The other one moving against its gradient, utilizing that kinetic energy. Is chemical energy required for secondary active transports? That is to say, is ATP required for secondary active transport? We've already said that secondary active transport utilizes kinetic energy, but do we need chemical energy in the form of ATP for this to happen? And this is somewhat of a theoretical or philosophical question, but it's worth talking about. And my argument is yes, it absolutely does. It doesn't need it immediately in the process of secondary active transport, but secondary active transport depends on things moving down their gradients. And so let's take a look back at the sodium glucose transporter. For the sodium glucose transporter to work, there needs to be a high concentration of sodium outside of cells and a low concentration of sodium inside of cells. If we did not have ATP, the chemical energy in the form of ATP, to power the sodium potassium pump, to keep pushing sodium out of the cell, to maintain sodium's chemical gradient, we would never be able to have kinetic energy. If the sodium potassium pump was not working, we would lose sodium's gradient over time. And I just realized that this should have an A right here, but this is supposed to be sodium. If we lose sodium's chemical gradient, we could no longer have sodium moving into the cell in this scenario, creating the kinetic energy needed to pull glucose into the cell against its gradient. So my argument is definitely we need chemical energy for secondary active transport. Certainly it's needed more upstream, but without chemical energy in our body, we are never going to have secondary active transport.